and space hope to find solutions that allow you to scale your networks further. Thank you.
So now I have the opportunity to ask you a few questions. That was really some very interesting innovation. And you said some very interesting things there about capacity. And I'm wondering if you can tell us a little bit about how you think that's going to affect, what kinds of people is that going to affect, and what kind of impact is that going to have?
So capacity is very relative. It depends on which operator you're talking about. Obviously, there are operators that have very low demand right now, but then there are also ones that have very high demand and at a very high growth rate. Web scales typically have huge growth rates in their capacity demand, so they will be affected first. Some incumbents might be affected later. But it depends really on who you are, what your network is, what your growth rates are. But with that table I showed, you can very easily just pick your favorite growth rate, pick the one that applies to your network, and see what that means in terms of a 10x and 100x technology increase over the years.
And so what kind of things should we be doing? What should we be thinking about to address these challenges?
Yeah, so that's a good question. And as you saw, there are 5 physical dimensions that we can use to further scale networks, and only 2 of them are really not exploited as of today. And that's frequency and space. In frequency, we can go to more amplification bands. Right now, we just have the C band deployed in optical systems. We can go to C plus L band, maybe C plus L plus S band. So a factor of 3 or maybe 4 might be possible with some luck. And if you go to those broadband systems, you can use sources like comb sources, for example, that to generate thousands of carriers at the same time. So very new technology that will come into play. And then once frequency is exhausted, you will really need to go to space, to the spatial dimensions, which to first order means parallel systems. I don't want to go into the more forward-looking scientific details of what spatial parallelism could mean, but we can take that at another time.
Okay, we'll definitely do that. So rather than going further into the future, let's talk a little bit about coherent. This was a key innovation that came from Bell Labs, and talk about how that technology, are there things that we can use, that we can implement from that chip, from the DSP chip, that would allow us benefits at the network scale?
Yeah, so coherent really changed the picture. Coherent changed the picture in the sense that 10G had problems on certain links already with polarization mode dispersion, chromatic dispersion, and everybody thought with 100G you cannot do that with the existing fiber. But with DSP, you can now electronically compensate for all kinds of possible impairments that occur on the fiber, linear and nonlinear impairments, and 100G becomes a piece of cake on a link where 10G had to struggle. So DSP is really something that opened up a lot of possibilities for existing links. At the same time, using DSP, you can open up new interfaces, you can monitor the network. For example, if you imagine a backhoe nibbling at the fiber somewhere, a construction site, the DSP will sense that. The DSP will sense a polarization rotation in the signal that corresponds to the backhoe digging up your fiber cable. So even before the fiber break happens, well before the fiber break happens, you can now send the maintenance crew or call up the police or do whatever you want with your SDN interface and send somebody there to look what's going on, or just proactively reroute the traffic to a safer route.
And does it allow you to do any other things to make it more open? As an example, how about alien wavelengths?
Yeah, so alien wavelengths means sending wavelengths of a different vendor than the one who actually built the line system over your system. And with coherent technologies, this is also much easier than it used to be, because, again, coherent can compensate for impairments much more easily. So there's a lot of flexibility on various fronts that allow for openness using coherent.
So this is a lot of very interesting technology. I'm very excited about the technology, but there's also a business component here. And I'm wondering if you can tell us a little bit about the early days of the transistor And it wasn't just the technology, but it was also the business environment that enabled that innovation, that technology to really take off. Tell us a little bit about that.
Absolutely.
Yeah.
So the transistor back then was such a breakthrough invention, and AT&T decided to give it away. They gave it away to industry in the US, to industry all across the world, even to academia. Executives from AT&T and Bell Labs back then went around with samples of transistors and handed them out for people to play with. So that device that was originally just meant to be a replacement for a linear amplifier had so many uses, including switches, as you all know, and now we have millions of transistors on a chip. That wouldn't have been possible without the freedom of giving away the intellectual property, essentially, and giving samples away for people to play with.
Yeah, so that's really a huge impact on the industry. So I think that's a really great accomplishment. I'd like to thank you very much for sharing your insights here on the innovation at Bell Labs. It's been very interesting. So once again, I'd like everyone to thank Peter Winzer.
Thank you.
Thank you.
Thanks.